why would this be true? I mean, we didn't prove it. Because I said so? Yeah. Darn it, I did say that earlier, right? Well, to be honest, you shouldn't have that attitude with anybody in your life. Because you don't want to believe anybody blindly. That's a bad idea. Not even your professors. Because some of your professors, let's face it, are crazy. Not Mr. Jones, not Mr. Chamberlain, but other professors are crazy, right? So I'd kind of like to maybe do an outline of the proof of this. Would that be offensive to some people? No. So let's write this down. Okay, so does everybody remember differential form? It stinks that we had a vacation in between this because you guys just, it fades away quickly. But let's rewrite this statement because I want to focus on the double integral and the differential form. So how would you go about proving this? I'm going to give you an outline of the proof. So the big outline would be this. You could do this. You could show individually that the line integral over C p dx is equal to the opposite of the double integral over R dp dy dA. That's just part of it, isn't it? And then you could also show that the integral of q dy, line integral over C, q dy, is equal to the double integral over R dq dx, dA on the end. And then sum to get the results, or the result. So now I haven't proved it, but what I'm saying here is you could split this up additively into two integrals. Obviously, you can split this up additively into two integrals. So if you individually you prove these things are true, you can add them up and get the result. Shouldn't come as a big surprise, right? We all know integrals are additive even in the new notation that we've developed. So let me just, I don't think that's quite enough. So let me at least prove this first relationship and then say that the other stuff is similar, just to give you an idea of how some of this goes. So proving it in its most general form would be difficult. But if we prove it for like a vertically simple region or a horizontally simple region, that's not actually that bad. So let's do it for a vertically simple region. Vertically simple region R. So if I draw a picture of that, what's a generic vertically simple region look like? Well, you're going to have maybe a function, call it g1. This is in the xy plane, g1, y equals g1 of x. Let me be specific here. Y equals g1 of x. And then you'll have a function like this, perhaps, y equals, say, g2 of x. And then you'll create a left-right boundary if they don't intersect. So maybe this horizontal value is at a x equals a, and this horizontal value is x equals b. And then inside here is our region R. Okay, and remember, what do we mean by a vertically simple region? Any representative vertical rectangle you draw on there is going to have the top of it given by G2 and the bottom given by G1, right? Okay. So let's compute generically this right-hand side, and you're going to start to see right away, right after we do the inner integral, how similar it is to the line integral. It'll become not all the way clear, but mostly clear. Or at least halfway clear, since it's half the statement, right? A solid third, okay. So let's see if you buy this then. That right-hand side circled in purple is this guy. Opposite double integral over R dp dy dA. Okay, what would be the appropriate inner limits of integration here? So look at this is good review for the final two, guys. Set up your vertical representative rectangle, bottom and top of which give you your inner limits of integration, right? So inner limits of integration go from g1 of x to g2 of x. Outer limits? A to b. And then the integrand is, okay, well, I'll leave it as dp dy for now, but remember, p is a function of x and y. We're just not writing that down right now. I will write it down in a minute. Oh, and let me go with dy dx, since it's a vertically simple region. So hopefully no big surprise there, right? Let's actually evaluate that inner integral. Does everybody see why we can do that without too much of a fuss? You're going to integrate a derivative and the derivative is with respect to y. You're integrating with respect to y. What's going to happen? You're just going to get p, right? Evaluated from g1 to g2. Would you buy that? Okay. So now I need to write p in its full glory. What do I mean by that? It's really p of xy, right? The components of the vector field in the plane are functions of x and y, remember. And then it's that evaluated from y equals g1 of x to y equals g2 of x, isn't it? And then we'll have this dx on the end. Question? Okay, so let's go ahead and just evaluate what we have here. Does everybody see, if I skip a step and bring in that negative and reorder it so the positive term's in front, what will it be inside? We'll still have the integral from a to b. Yeah. Yeah. So we're plugging in for y, right? We're plugging the g functions for y. So if I distribute that negative essentially and reorder, I will have p of x and then g1 of x. P of x comma g1 of x. Does everybody see that? Minus p of x comma g2 of x. Everybody agree with that? Does everybody see the step I kind of skipped a little bit? Okay. Then dx. Now I'm going to stop there. But notice already in this step, hey, this guy, except for the negative, kind of already looks like this guy a little bit, doesn't it? Notice we have p and we have a dx, an integral, yeah? Okay. So we're part way there. So now all I'm going to do is prove that the left-hand side I just circled in red is equal to what we just got here in this last line. So let's start with that. So we're done evaluating the right-hand side. Now it's time for the left-hand side. Now, going back to the picture for a minute, I'm going to remember we have to orient counterclockwise, right? So this actual region R is comprised of 4 curves. I'm going to orient all 4 going counterclockwise as viewed from above. And I'm going to call this bottom one C1, this side one going counterclockwise C2, the top one C3, and the bottom, or the left one rather, C4. Okay. And so somehow I want to get a statement. So what do I want to do? I want to take this guy I encircled in red, and I need to leave myself some room here, so I'll try to start right here. Somehow I want to rewrite this guy so that it looks like this guy. And then I'll have the part of the proof that I'm after here. So, well, how do we evaluate a line integral? Now you got to think back, okay, evaluating line integrals, how do we do that? What do we need? We need a parameterization, right? Yeah, for our curves. And we need to realize that, oh, we're going to have to split this up into 4 line integrals because C, this thing I'm calling C right here, is going to be the union of C1, C2, C3, and C4. Thankfully, A couple of them will be 0. A couple of the line integrals will be 0, right? So the first thing to realize is then, oh yeah, this splits up additively. It's going to be the integral over C1 plus the integral over C2 plus the integral over C3 plus the integral over C4. And right now you're thinking, oh my gosh, what did we get into? Well, 2 of these are 0. And even without parameterizing, I bet I can convince you that that's true. Do you notice that C2 and C4, the differential has to be 0, doesn't it? When it's a straight vertical line, dx in other words. Yeah. So I think without a whole lot of thought, we can say, well, this guy is 0. Wait, wrong one. This guy's 0, C2 and C4, and this guy's 0. Okay, so now we've got it down to 2 integrals. Whew, thank gosh. All right, well, we don't have to parameterize in terms of t, right? We can just let x equal x. And then the function for the bottom curve, if we just, for C1, if we just let x equal x, remember in the past I said let x equal t, the parameter. You didn't have to do that. You could just let x equal x. It doesn't matter. And then automatically, what's y? Then y is, in this case, g1, right? Would you buy that? Oh, all right. And then I think we could just directly plug in. So for C1 then, what does x run from? A to B, right? You could do something similar for C3, but you have to go back the other way, don't you? So you can think of, even though it's weird to think of it this way, you can think of x as running from, I'm not sure I want to write it this way because it definitely wouldn't be true as far as inequalities go, but when we set up the integral, we can say x goes from B to A, and the parameterization is just x equals x and y equals g2 of x. So I'm going to avoid writing that down, but hopefully that's not too big of a surprise, right? So now let's set up our integrals. We have the integral, okay, C1 goes from A to B, right? P of x comma y, but what's y? G1 of x. dx won't change since x equals x, right? dx equals dx. Okay, we're almost there. Plus this guy, you have to initially set it up from B to A, right? But luckily there's a negative that we're going to want, aren't we? So it's going to work out. So it would be P of x comma on C3, it would be y would equal g2 of x, so g2 of x, and you guys can see it working out hopefully pretty nicely so that we could rewrite this as the integral from A to B, just copying, recopying this part down, and then I'll make this a minus to change the limits of integration to A to B. dx. And then you can see, oh, as soon as we combine it into a single integral, we get the result, don't we? So this does it for the first part of the proof. Thus, so that what did we just prove? Oh, we just proved that the integral over C, p dx is equal to the opposite of that double integral. And that's over R. Now, that's not the whole proof, is it? That's not the whole proof, but I would just say that this part is similar, and then sum to get the results. Okay? So I know you guys all look thrilled, but I felt guilty that I didn't prove much in this chapter, so there you go.